Lately, we have been talking about boundary conditions. So I have this example where two dielectrics meet on plane z equals 0. So that z equals 0 plane, that's the horizontal plane. So if you want to think of it just kind of like this, here's our z equals 0 plane. And for z greater than 0, so that's up here, so this is material 1, the relative permittivity of material 1 is 4. So we've got material 1 up there. And then for z less than 0, so that's down here, the relative permittivity is equal to 3, material 2. So a uniform electric field, E, given by this thing here, kilovolts, notice kilovolts per meter, exists for z greater than 0. So what they give us, this electric field, is for material 1, that's up here. So they're giving us this E field up here. That's a terrible E. My pen has not been working very well. One second. My tablet pen has not been cooperating very nicely. Okay, that's better. That's better. All right, so part A, we're going to find the electric field for the other material then. So that would be the incident material. And so let's just start there. So remember what we said about boundary conditions, how we have to break this up into the normal component and the tangential component. So let's ask ourselves, what is well, first of all, the interface is along the z-axis. So or not along the z-axis, but it's perpendicular to the z-axis. So the normal component is along the z-axis, and the tangential is here. And so we look at what we're given, and we're going to call that E, what we're given there, we're going to call that E1. So I'll put the subscript E1 because that's in material 1. So we ask ourselves, well, what is the normal component of E1, right? And well, you can do the dot product and so on, but we know that the normal component is the component in the z direction. So just by inspection, I can look at this, I can say, well, the normal component is 3 kilovolts per meter. Okay, and then the tangential component is what's left, right? Because the tangential plus the normal must add up to they must add up to the original electric field. Okay, so we have that, and that's in kilovolts per meter. Okay, so what did we say about the boundary conditions and how the electric fields are related in the two materials? Well, we said, and we showed why, we said that the tangential components are continuous, right? That is to say, the tangential components are equal to one another at the boundary. So that means that the electric field, or the tangential component of the electric field in material 2, okay, E2t, is 5ax minus 2ay kilovolts per meter, like that. And then what did we say about the normal components of the electric field? Well, they are discontinuous. And how is the normal component in the second material related to that in the first material? Well, that would be, as we showed, that would be the relative permittivity of material 1 divided by the relative permittivity of material 2 times the normal component of the electric field in material 1. And so that, as a vector, that is 3az, right, kilovolts per meter. Okay, so I punch in the numbers, right, 4 over 3 times 3, so this gives me 4 az kilovolts per meter. And so I've got the normal component in material 2, I've got the tangential component in material 2, so that means that the electric field in material 2 is just the sum of those, 5ax minus 2ay plus 4az, And again, that's in kilovolts per meter. So there we go. That was part A. All right, so now we look at B. B wants to know the angles the electric fields make with the interface. So the electric fields plural, so we're talking both E1 and E2. So E2 comes in like something like this maybe. Right? And so we want to know, what is this angle here? Right? And similarly, what is this angle? Right? Okay, so let's see if we can find those angles. So let's get theta 1 first. So theta 1, remember when we're dealing with vectors and we want to find angles in between vectors, then we should rely on the dot product. And in particular for material 1, if I take the dot product of E with a unit vector that goes normal to the boundary, that is AZ, then I can get the angle in between AZ and the electric field. So what I'm going to do here is take 5AX minus 2AY plus 3AZ, right? That's the electric field 1, dotted with AZ. And why am I choosing AZ again? Because I want the angle that E1 makes with the z-axis. AZ is a unit vector that points along the z-axis. Okay, and then by the definition of the dot product, so this is the geometric definition of the dot product, that is the magnitude of both of those vectors times the cosine of the angle in between them. So the magnitude of E1, okay, times the magnitude of AZ, well, AZ is a unit vector, so its magnitude is 1, times the cosine of the angle in between them. So this is theta 1 here. All right, so if I want theta 1, of course, well, I can get the cosine of theta 1 is equal to 3. Why 3? Well, 3 is the dot product. So if I carry out this dot product, AZ times AX, or dotted with AX, is 0 because they're orthogonal. AZ dotted with AY is 0, similarly. And then AZ dotted with AZ is 1, and I pick up that 3. So 3, and then I divide it by the magnitude of E. So what's the magnitude of E? Well, that is 5 squared plus negative 2 squared plus 3 squared, right? All right, so that is 3 over, looks like root 38, 25, 9, 4, yeah, square root of 38. And then I can plug that in my calculator, take the inverse cosine, and I get 60.9 degrees. And I want to point out that's rounded to 3 significant digits. And why that's important is when I go to get theta 2. Now, how am I going to get theta 2 from this? Well, the law of refraction tells me how theta 1 and theta 2 are related. So tangent of theta 1 divided by the tangent of theta 2 is equal to the ratio of the relative permittivities, right? Epsilon E1, epsilon R1, epsilon R2, like that. And so what I can do is do some cross multiplying and solve for tangent of theta 2. Tangent of theta 2 is the relative permittivity of material 2 divided by that of material 1 times tangent of theta 1. Now here I'm going to do a little trick with the triangles and get theta 1, because I'm not going to plug in 60.9 degrees into theta 1 here because that's rounded, and so that rounding error then would propagate through to my new calculation. So I'm not going to do that. I'm going to set up a little triangle, which you should have been doing this in your math courses previous to this course. If I know the let's see, let me back up, the cosine of my angle, so I'm just going to call this theta 1 for right now. The cosine of my angle is 3 over square root of 38. So the cosine is adjacent over hypotenuse. So adjacent over hypotenuse, 38, right? So by the Pythagorean theorem, then what does that make this side? That makes that side the square root of 29, right? Because if I did 3 squared plus root 29 squared, that would give me 38. Take the square root of that, that gives me that length. Okay, so now I want the tangent of theta 1. The tangent of theta 1 is opposite over adjacent. So that would be root 29 over 3. You see that? So now I plug in epsilon for material 2. So that is 3. And then for material 1 is 4. And then I've got square root of 29 over what we said 3. Yeah, opposite over adjacent, root 29 over 3. The 3's cancel, and I have an exact number for my tangent of theta 2. Okay, so then I go to the calculator and I get the inverse tangent of theta 2, and I see that the inverse tangent gives me theta 2 is equal to, up to 3 significant digits, 53.4 degrees. That's my answer. So now I've got the angles the electric fields make with the interface. All right, so I'm going to try to squeeze part C down here. So see, I'm looking for the energy density in each material. So that's little w1, WE1, excuse me, and we showed in a previous video that that is 1/2 times the permittivity of free space times the relative permittivity of material 1 times the magnitude of the electric field squared in material 1. Okay, so I just plug in those numbers, being careful about the prefixes and so forth. So this is 8.854 times 10 to the minus 12. You have that memorized yet? And then times 4, right? The relative permittivity for material 1 times the square of the magnitude of the electric field in material 1. So we found that to be square root of 29, or no, not square root of 29, square root of 38. And so when we square that, we get 38. And also, I want to point out that the electric field was in kilo. So when we square it, we actually get times 10 to the 6th. So you got to be careful there. We had kilo volts per meter. Squaring makes 10 to the 6th. And so when I carry out all of that calculation, I get 672 microjoules per cubic meter is the energy density in material 1. And similarly, if we do this in material 2, we get 597 microjoules per cubic meter. So that is our answer. Okay, so finally, in part D, we are asked to find the energy in a cube with specified by its center and its side length. So let's do that. So part D, energy in a cube. Okay, so the first thing that you need to ask yourself is, does this cube cross the boundary? Because if it does, then we need to divide the cube into 2 segments, right? 2 parts. So the center of the cube, and really what's of importance here is the z-axis, because the z-axis is defining where our interface is. Not the z-axis, excuse me. The z equals 0 plane. So that's what we need to concentrate on, the z number here, -5. So it's centered at -5 on the z-axis, and so each side is 2 meters, which means if the center is -5, it goes up 1 meter and down 1 meter from -5. And so the highest this thing gets on the z-axis is simply -4, right? It goes -4 to -6 on the z-axis. All of that is to say then, it it entirely lies, the cube that is, entirely lies in material 2. It does not cross the interface. So we don't need to divide this into two parts. So while it lies entirely in material 2, then what we can do is we can take the energy density in material 2, okay, which we calculated, and this was rounded, so we would want to recalculate this number carrying out more than 3 significant digits. But that's in joules per cubic meter, right? So then if we just multiply by the cubic meter, or the volume of the cube, then we have the total energy. So now this is capital W. Okay, so 597 microjoules per cubic meter. And then again, I'm writing it as 597, but really I'm carrying through the digits on my calculator. And then I multiply by the volume of this thing. So what is the volume? Well, each side, it's a cube. Each side is 2 meters. So this is 2 cubed, right? 2 cubic meters. And so this gives me 4.78 millijoules. And that is my final answer.